Hi, this is Geometry, Lesson 4-4, Proving and Applying the ASA and AAS Congruence criteria. In this lesson, we'll be able to determine congruent triangles by comparing two angles and one side. Let's look at exploring reason. Are these triangles congruent? Using only the angles and sides marked in the diagram, can you prove the triangles are congruent? No, the angle is not known between two given sides, so we cannot use SAS. We can't use SSS either since only two sides are known. So what do? What information do we need? What other values can you easily find? The third angle measure of each triangle, because we know two measures, we can easily find the third measure of the angle using the triangle angle sum theorem, right? So what theorem can you use to find a counterexample to the assumption? Let's look at part A first. Assume the triangles are not congruent. What contradictions can you find to contradict your assumption? Okay, let's first find the missing angle. What is the missing angle? Well, you have to subtract 180 by 65 and 45. And 65 and 45 together is 110. So the angle that's left over is 70. And notice that the two angles that are given are the same. So all the angles are the same. Using the SAS triangle congruence theorem, the triangles must be congruent. So we cannot, the assumption that the triangles are not congruent would be wrong. And this is how we can prove by making a contradiction. So how? You can say the assumption that the triangles are not congruent is contradicted by finding the missing angle and showing the triangles are congruent by SAS theorem. Okay. Is it sufficient to say that the triangles are congruent because of the contradictions we found? Yes, it is. By SAS theorem, the triangles are congruent, right? So using the triangle angle sum theorem, we know that the unknown angle measures are both 70. And if we have the same angle measures and the same side lengths, then we can use SAS to prove that they're congruent. So yes, that's enough. And also, if you want to prove further, then by CPCDC, the unknown side lengths are also congruent. So you can use both SAS and SSS to prove that they must be congruent. This contradicts the assumption and shows the triangles are congruent. So in this lesson, we will think about how the ASA and AAS are used to show that the triangles are congruent. We don't know what ASA and AAS are yet, but we will learn that today. Let's look at example 1. Explore the ASA congruence criterion. How many possible triangles can you determine when given two angles and an included side? It is important that the side is included. So let's try to draw different triangles. If you have a specific side length and specific measurements of the two angles at the end of the side, then there is no way other than one to make different triangles that have the same information. Because, so look at this diagram. We have AB that's 3 centimeters and BAE is 25 degrees. If we know the other angle must be 57 degrees, then there is no other way than to have the middle triangle, because if we have different angles, the sides are not going to match up, right? It needs to have exactly the right angle. Wait a minute. Yes. So if you have two angles and one included side, there is a unique triangle. There is only one way to draw that triangle. So let's try number 1. What's the relationship between AXB and AYB? Are they congruent or not? Look at the angles. We have two angles that are congruent, 25 degrees and 45 degrees. The included sides are also 3 centimeters. So by using the theorem that we just looked at, the ASA congruence criterion, the triangles must be congruent. Although they have different orientation, one is looking to the left, one's looking to the right, the triangles are congruent. So how can we say using the a rigid transformation? How can we prove the congruency using the theorem, but also we can describe it using a rigid transformation? What would this be? Triangle AYB is a reflection of triangle AXB over a vertical line. By ASA, the triangles are congruent. Sweet. Let's look at this theorem. ASA congruence criterion. If two angles on one side, one triangle and the included side are congruent to two angles and the included side of another triangle, then the two triangles are congruent. So it must be the included side and two angles, okay? And example 2 proves this theorem. Okay, we're given two angles that are congruent and the included side that are congruent. We can use rigid motion to map the triangles. Then we'll be able to prove that the two triangles are congruent by the definition of congruency, right? We can define it using rigid motions. So from MLN, we translate to map M to S. So we move it. We move this triangle down here, okay? And then we rotate about point S, okay? So that it's exactly here. And then we reflect it over line MT or ST, okay? So because angle measures are preserved with reflections and rotation and translation, we have two triangles that are congruent. So let's try number 2. Describe a series of transformation that shows triangle JKL is congruent triangle MNO. Okay, do the triangles have the same orientation? Is it necessary to reflect the figure to get a mapping, or questions that you might ask before describing a series of transformations? So how can JKL be mapped to triangle MNO? Start with a translation and then a rotation, and if reflection is necessary, reflection. So let's try to translate JKL to map point K to N. Okay, we're going to translate it here. Okay, and then we have this part. Does that make sense? So when we do not have a coordinate point or coordinate plane to describe the rules of translations, then we have to specify the points mapping to specifically which point, okay, and which line. And then we're going to rotate about point N to map KL. Wait, is this K? Yes, KL and K. Yeah, we're going to map KL onto NO and point J to M, so it fits perfectly. Yes. So they're the same orientation and you don't need to reflect this figure. So we're just going to translate and rotate. But make sure you describe the point of rotation. About. And to map KL to NO and point. So at last, you have to check if all the points are aligned and mapped to the corresponding points, and it does. So we're done. Let's look at the next page. We're gonna look at example 3. Apply the angle, side angle, congruence criterion. A technician installs cables from a cell phone tower to the ground. To pass inspection, both cables must be the same length. Does this installation meet the cable length requirement? Explain. So look at the picture. We have a cable here, that's the tower, and another cable here. And both cables have 52 degrees angle from the tower to the ground. Okay, what assumption is made in solving this problem? How does that affect solving the problem? Well, the solution assumes that the tower is vertical, so that's the right angle, and that the ground is horizontal, right? If this were not true, the two angles with vertices at point X would not be right angles. So that's what we need to assume first. And then we're gonna identify the triangles, right triangles there. So we got two angles here, 90 degrees and 52 degrees. And we know that the tower is congruent to itself. So we have the congruent sides for these two triangles. Okay, so all right angles are congruent, 52 degrees are congruent. By the reflexive property, the tower is congruent to itself. So we got two angles and one side that is between the two given angles. So we can use the ASA triangle congruence theorem to prove that these two triangles are congruent. And by CP/CDC, AB is congruent to CB, and both cables are the same length. So yes, the cable lengths do meet the inspection requirement. Let's look at try question number 3. Part A, are triangle JKL and triangle MNO congruent? Explain. Part B, are triangle JKL and triangle PQR congruent? Explain. Okay, come back when you're ready. So look at the triangles JKL and MNO. Right, what properties can you use to show angles are congruent and the triangles are congruent, right? JKL and MNO are the points corresponding to each other, JKL and MNO. So yes, K and N, they're corresponding angles and they're congruent. J and M are corresponding angles and they're congruent. And JK and MN are corresponding sides and they're congruent. So by angle side angle theorem, ASA, triangles JKL and MNO are congruent. Okay. What about JKL and PQR? Let's see if they're corresponding to each other. JKL, PQR. So that's corresponding to J, K, and L, right? J and P are corresponding angles and they're congruent. K and Q, they're corresponding angles and they're congruent. But we do not know if JK, the line JK is congruent to line PQ. We just know line QR is congruent to the other sides that are in between these angles. Because line QR is not between the two angles given, we cannot use the ASA theorem. So no, they're not congruent because MN is the included side, but QR is not. Okay. Let's look at example 4. Investigate the angle side congruence criterion. Given triangle ABC is a triangle determined by angle A, angle B, and the non-included side AC unique. Assume that triangle ABC is not unique, then there must exist triangle DEF such that triangle ABC and DEF is not congruent, because if it's not unique, then they don't always have to be congruent, right? Even if they have the same angles and the same side. So we're given that angles A and D are congruent, B and E are congruent, and sides AC and DF are congruent. Okay, by the triangle angle sum theorem, 180 minus A and B should be angle C, and angle F should be in the same way. Angle F should be 180 minus D, measure of angle E and D. So since they're A and D are congruent, B and E are congruent, measure of angle C is really equal to measure of angle F. So the angles C and F should also be congruent, right? So by SAA, ASA, the two triangles must be congruent, and the assumption is false. A unique triangle is determined by A and B and the non-included side AC. Okay, so even if the side is not included, we have a unique triangle, and this is a different theorem, AAS. Okay, so using the figure shown in triangle number 4, describe sequence of rigid motions that maps triangle JKL to triangle QRP, because we know those two triangles are going to be congruent by AAS. Can we figure out the sequence of rigid motions? Okay, start by translating JKL. We're going to translate this so that we map K to point R, to the point that it's corresponding to. Okay, so we're going to translate triangle JKL to map point K to point R. Then what do? So after we do that, we have a triangle here. Do we reflect it or do we rotate? Think carefully. We just translate it. So we just move just where it is. Okay? J and Q are corresponding angles. So if we reflect this, then J is going to map onto P, which is not a corresponding angle. So we have to rotate it. Okay? So we're going to rotate triangle J prime, K prime, L prime about point R to map lines KL to PR and point L prime to point P. Okay, and now we have two rigid motions that describe that map the two triangles. Let's look at theorem 4-7. Angle side congruence criterion is the theorem that we just looked at. So if two angles in a non-included side of one triangle are congruent to two angles in a non-included side of another triangle, doesn't matter which non-included side it is, whether or not it's on the left or the right, it could be a reflection, right? So it doesn't matter. If two angles are congruent and one side that's not included is also congruent, then you can use AAS, triangle congruence criterion. Okay. Example 5, we're going to use triangle congruence criteria. So far in this lesson, we learned ASA and AAS, right? In last lesson, we learned SAS and SSS. So using all these theorems, can we prove the triangles if they're congruent? So look at these examples. These two triangles are congruent by ASA, angle, and then their side in between, so ASA. These triangles are congruent by SSS. These triangles are congruent by AAS, okay? The side is not included. And these two triangles cannot be determined. The angles are not corresponding to each other, right? So if you look at examples, examples of triangles, can you determine which theorem are you going to use? And proving that a part is equal to another corresponding part, you first usually have to prove that the two triangles are congruent, and then use the CP/CTC to prove that the parts of the triangles are congruent. So look at this example. This is a short proof and short example of how you can prove that the sides FH and JL are congruent. Okay, we're given two angles that are congruent and a side that's congruent. So using those information, we're going to use AAS to prove that the two triangles are congruent. And by CP/CTC, we're going to prove that FH is congruent to JL. And that's it. We just have 3 steps, right? So look at try question number 5, A and B. What additional information is needed to show triangles ABC and DEF are congruent by ASA? If you want to prove it by the theorem ASA, which additional information do you need? Remember which information you're using for ASA. You need two angles that are congruent and the included side. So we already have angles A and D that are congruent and a side. And we determine which angles of each triangle would make the given side the included side, right? So part A, you're going to need the angles B and E. And they must be congruent to each other. How about part B? What additional information is needed to show those two triangles are congruent by AAS? You need two angles and a non-included side. Okay, in order to make those given sides that are congruent non-included, we need the other angles to be congruent, right? The other angles are C and F. All right, let's look at the last example, example 6. Determine congruent polygons. All sides and angles of A, B, C, D are congruent to the corresponding sides and angles of A prime, B prime, C prime, and D prime. Is A, B, C, D congruent to A prime, B prime, C prime, D prime? Okay, so ABCD is a quadrilateral, but quadrilateral could be divided into two triangles. Yeah. So look at these quadrilaterals that are cut into two triangles. Triangle ABC is congruent to A prime B triangle ABC prime by SAS, right? And also, in the same way, triangle ADC is also congruent to triangle ADC prime. Since the two triangles are congruent, then yes, the quadrilaterals should be congruent, right? So you can determine if the polygons are congruent by using the triangle. So cut the polygons in half or in 4 pieces, or how many pieces you like to make triangles that are congruent. So let's look at try number 6. Given ABCD is congruent to EFGH, what is the value of X? If they're congruent, that means all the sides using the CPCGC, all the sides are congruent, corresponding sides are congruent, all the corresponding angles are congruent. So A is congruent to B, just one dash. A and E are congruent, okay? B and F are congruent. C and G are congruent. And D, okay, let's use another color. D and H are congruent, okay? And the sides are congruent as well. AB is congruent to EF. BC is congruent to FG, okay? CD is congruent to GH. And then DA is congruent to HE. Okay. So what's the value of X? We know that EH is congruent to AD. AD is 9 meters. So 9 meters should be equivalent to 2x minus 3. Now we have an algebraic expression that we can solve for it. Add 3 on both sides. And then we have 12 is equal to 2x. Divide 2 on both sides. And we have x is equal to 6. X is equal to 6 is our answer. That's it. All right, so what did we learn in this lesson? We learned more theorems about triangle congruency. So theorem 4-6 is the angle side angle theorem, having 2 angles that are congruent and the included side that's congruent. Theorem 4-7 was about angle side, where we are given 2 angles that are congruent and 1 non-included side that are congruent. Okay. So that was lesson 4. Lesson 4-4, proving and applying the ASA and AAS Congruence criterion theorem. We'll continue with the next lesson in the next video. Bye.